So good afternoon, everyone. It's an early morning for me, and thank you for that great introduction. And so what my presentation today is going to be, it's going to be more focused on broilers, but for the guys in the pullets and for rearing and breeders, the concepts are exactly the same. It's just that we have slightly different requirements in terms of heat loads in houses. So before we start actually getting into the presentation, I will jump around a little bit between imperial numbers and metrics. So for any of you that get a little confused, simple conversions, a square meter, there's 10 square feet in a square meter, there's 35 cubic feet in a cubic meter. And if you talk about static pressure, here in North America, mainly we speak about inches of water column. To convert, just simply multiply by 250. So 0.1 inches of water column is going to be 25 Pascal. So what we have is a presentation broken down into what I'm going to try explain, or what to achieve in the presentation is looking at why we have a certain amount of fan capacity for hot weather, and why do we insulate houses, and what are the important factors around that. So I'm going to give you a kind of a very brief overview of why we have air velocity in the houses. And to understand that, we've got to understand three or four different factors. We would need to understand how much heat does the chicken produce and how do we remove that heat from the chicken. Second of all, we've got to understand the insulation properties of a house and how heat enters the house. And very, very important, and I'm sure Brendan spoke about static pressure in his cold weather presentation, understanding the concept of static pressure in tunnel ventilation scenarios is also fairly different. And then in the importance of the cooling system and how important it is to keep the house at a certain temperature. So to start off with, we got to talk about the thermoneutral zone. Everybody has heard about thermoneutral zones. So at Hatch, we tend to say the thermoneutral zone for a baby chick is 32 degrees Celsius. That's where it's most comfortable. That's its optimum zone. As they get older, that thermoneutral zone will decrease. So maybe at 28 days, we could say the most comfortable for that chick would be 24 degrees C. Now, if we start moving into a scenario where it starts to get cool, then we need to add more energy to keep the chicks warm. And the opposite happens when we increase the temperature in the house. But what we're going to find is in hot weather, even if we design the best houses, we will never be able to keep in hot weather chicken at its absolute optimum. We're always going to be slightly in the hot side, but we're never going to move to the heat stress scenario. So when we design the house, we really got to think about how close can we get that bird into its thermoneutral zone to get the optimum performance. So the most important part is removal of heat. And we know that once the temperature difference between the chicken's body temperature and the surrounding air temperature narrows or becomes smaller, we need to remove more heat. And how do we do that? We use what we call the wind chill effect. So we actually incrementally increase air movement to create this wind chill effect to remove the metabolic heat from the bird. We know the surface temperatures of the chicken at hatch are going to be somewhere close to 39, 40 degrees C. And an older bird, it's slightly higher. So when we look at broiler heat production, we really have to look at, in terms of BTUs per hour per kilogram, how much heat or how much energy is produced by the bird. And as the bird ages, as the bird gets older, we find the amount of BTUs per kilogram per hour decrease. So we would assume that a larger broiler or larger pullet produces more heat in terms of BTUs per hour, but it's the opposite effect. And why is that? It's simply in terms of feed intake. As the broiler ages, and as you can see on this little graph I have here, on the horizontal axis, we have body weight. The vertical axis, we have BTUs per hour per kilo. And on the right-hand side, we have another axis that shows you feed intake as a percentage of body weight. So as the bird gets bigger, its intake as a percentage of its size decreases. So that's why we see BTUs per hour per kilogram of the 1.8 kilo bird is less than a baby chick. So where does a broiler or any bird release heat? It's going to be on the head, the legs, under the wings. So if you have a look at a thermal image, it's very clear where that bird is going to be losing its body heat. So let's look at 3 scenarios, and I'm going to go through these and to explain how the bird thermoregulates. So we look at it, this is a 2.2 kilo, a 5-pound broiler in a chamber under experimental conditions. And they're looking at how the bird partitions its heat, how the bird maintains a steady body temperature. So if you look at this bird, and this bird is in the chamber at 21C, it's at its thermoneutral zone. It's close to what is most comfortable. So in terms of heat loss, we know that 40 to 50% is going to be lost to the surrounding air in the house. That is what we call the sensible heat loss. 50, you could say 60% of its heat is going to be lost through panting, evaporative cooling. So in this experiment, 34 BTUs is going to be lost through evaporation in the respiratory tract. 26 BTUs per hour has to be lost through sensible heat loss. So that's 60 BTUs per hour. That's what the bird has to release to keep itself in the thermoneutral zone. When the bird releases heat in terms of evaporative cooling in the respiratory tract, that heat is given off as water vapor. It's given off as humidity. So that adds humidity to the house. But the sensible heat portion is very important. That's the portion we have to remove from the house. That is the portion, the 26 BTUs per hour is what we as managers have to ventilate out the house. If the temperature drops in the house, in this example, we're looking at 15 degrees C environmental temperature, it still will produce 34 BTUs per hour in the evaporative tract. It's going to produce that amount of energy. But because the temperature around the bird has now dropped, it's going to lose more heat. And in this experiment, it lost an extra BTU. So instead of 26 BTUs per hour, the body temperature, because of the differential between the body temperature and the surrounding air, the bird started to cool. So it lost a total of 61 BTUs. If you keep the bird in this environment for a long time, it will slowly reduce its body temperature. We're going to have to add more heat to the house to keep the bird in its thermoneutral zone. So what happens if we increase the temperature in the chamber? If we increase it to 29 degrees Celsius, what are we going to expect to see? We're going to expect the bird to pant more. It's going to try thermoregulate by using evaporative cooling. So this example, the bird was losing 39 BTUs per hour that was released in terms of evaporative cooling. 15 BTUs per hour is lost through sensible heat loss. That narrowing of the differential between its body temperature and the surrounding air means that it's going to have a surplus of 6 BTUs per hour. It's only losing 54 BTUs per hour. So over time, body temperature will increase. So when we talk about thermoregulation, we've got to really understand how the bird naturally releases body heat. Now, if we throw humidity into the equation, we know that once we increase relative humidity beyond the 85% mark, the function of evaporative cooling diminishes rapidly. So that's why when we talk about evaporative cooling systems in broiler houses, in pullet houses, in production houses, we need to understand the minute we run our evaporative cooling, we will have 80 to 85% humidity in the house. So we have to have some way of taking away internal temperature of the bird by use of air exchange, by sensible heat loss. So let's look at an example. We're going to run through a little bit of math, and I hope everybody can follow, and it's not too late in the day. I'm early and I'm fresh. So if we look at a house and it's 50 meters wide, it's 150 meters long. So we have an area of 2,250 square meters. We're going to stock this bird at 21 birds per square meter. We're going to kill this bird at 1.8, and we're going to place 47,000 broilers in this house. So how many BTUs is going to be produced by those 1.8 kilo birds? Simply, we take it from the graph. You could argue it's probably, if you ask a nutritionist, they probably will argue it's not this amount. But for our intent, our purpose, let's say it's 30 BTUs per hour per kilo. So that means 54 BTUs per hour is going to be produced by this broiler. But we don't need to take away that the portion that's lost. If we say that the bird is losing 60% of its heat through evaporative heat loss through the respiratory tract, we only need to remove the 40%, the heat, sensible heat produced by the bird. So if we look at this example and we say, okay, 40% of 54 is 22. That's how much BTUs per hour that we need to remove per bird. So the total sensible heat loss to remove from that house, multiplied by the amount of chicks in the house, is going to be somewhere in the region of 1 million BTUs per hour. So what does that mean? How much is 1 million? So if you want to make a simple comparison, it's the same as running 4 forced air heaters all the time. So if we ran 4 of those box heaters, the LB Whites, rated at 250,000 BTUs per hour, it's like turning on 4 heaters and running them continuously. So that's the amount of heat or energy we need to remove from the house. So when we talk about heat removal, we always think about tunnel ventilation, but we forget about the transitional, the power ventilation mode. And Brendan would have spoken to you about cross ventilation systems. But as we move away from the timer ventilation stages, we start to remove heat from the house. We are essentially removing heat from the birds, the heat of production. So in transitional power, we're going to use about 40 to 50% of our tunnel fans in full transition mode. We're going to be utilizing up to half of our tunnel fans. So we have an air exchange in full transition mode of somewhere in the region of 2 to 3 minutes. In terms of CFM per square feet, it's going to be somewhere between 4 to 5. The very important part of this transitional system is that when we run transitional ventilation, we are removing heat from the house. We're keeping the birds comfortable, but we're not creating air movement at floor level, or we're creating very little air movement at floor level. So we're removing BTUs without the wind chill effect. So the transitional system is extremely important in all housing types, whether you have pullets, broilers, or production house, in cold conditions to make the birds comfortable. If you don't have inlets and you run your full transition mode, you can expect your air velocity at floor level to double. So how are we utilizing the system? So in the final stage of transition, most of the new controllers today will allow you to utilize the tunnel inlet along with the perimeter inlets. So what we tend to see more and more is, instead of moving straight from transition mode into tunnel mode, we have what we call a in-between mode. It's called a tunnel assist mode. Some companies will refer to it slightly differently, but what essentially it's doing is we're keeping our inlets at the full open 100% position, but we're bringing on more capacity just with our tunnel fan and opening the tunnel inlet, whether you have a curtain or a door, to compensate for static pressure. That way we can have heat exchange, we can have heat removal from the house without creating excessive air movement at floor level. So it's an excellent tool to use when the conditions outside are close to your target temps in the house. So in this video, what we're seeing is a house in full transition mode. What do we see? We see activity, we see feeding, we see drinking. So when we run in full transition mode, you see the inlets are fully open. We have a good air exchange. We probably exchanging that air every 2 to 3 minutes. But what we're having is heat removal. We have comfortable chicks which are eating and drinking. Everybody knows, or all the guys in the broiler industry for sure know, that the minute you start running tunnel ventilation, you change activity. So this house, we had 2 tunnel fans on, full transition mode, but instantly the new tunnel fans, 2 more tunnel fans come on, and what we see, and it's instantaneous, the birds go down. The minute you put those extra movement across the chicks, they respond very quickly. They stop drinking, they stop eating. So when you don't have consumption, you don't have growth, you have poor uniformity. So the big question is, can we run air speed on young birds? And the answer is yes, we can. So we have and I think it's in our broiler guide, we have a guide in terms of how much velocity will a young chick tolerate. So we know as managers from experience that in the first 5 days, somewhere between up to 0.3 meters per second or 60 to 100 feet per minute is acceptable. In the second week, 0.3 to 0.5. And once we go into up to 21 days, they will tolerate up to 1.8 meters per second. Now, this is when the temperature around the chick or the bird is similar to the target temperature. The minute you increase that differential between, you narrow the differential between the body temperature of the bird and the incoming air. So if your temperatures outside are 36, 37, and even 38 degrees Celsius, you can break the rules. You will have to run more velocity across these birds because we've narrowed that differential. This table is generally looking at if we are close to target, maybe 30 to 32 degrees C outside. But the minute we move into higher temperature ranges, yes, we will break these rules and the birds will not respond negatively. So yes, we can run air across young chicks in extreme conditions. So how does the guys in Europe, and I just thought I'd put this in for interest, and I know Brendan should have covered it. When we talk about cross ventilation or perimeter ventilation in cold weather, we bring an air jet in and we shoot it up and we follow the ceiling. But what do the guys do with our tunnel ventilation mode? What do we do if we don't have access to tunnel inlets? So what we have to do is we have to somehow have an inlet that allows you to push air down from outside onto the birds, and we create a rotational effect. And you can see in this illustration, this is your cooler air coming in from outside, and somehow we have to have a deflector on the top of our inlet to push that air down to bird level, create this opposite rotation effect. In cold weather, we rotate clockwise. In warm weather, in this type of house, we will do an opposite rotation. So what you have to have is an inlet with some form of deflector to push the air down to the birds. And this is a really nice video, and it's showing how they achieve this. This is a big house in Europe, and I think in the UK. And what he's showing you is he's smoking that house, and he's showing you that under full ventilation, summer ventilation, he's creating that opposite return. He's moving air across the birds from both sides of the house and creating an opposite rotational effect. And you can see, there we go. That's that opposite rotational effect. And that's the only way, if you don't have tunnel ventilation, to keep birds comfortable in extreme weather. I thought I'd just include that just out of interest, but I know some of the houses in South Africa don't have tunnel ventilation. So first of all, I've spoken about removing metabolic heat from the bird, keeping the bird close to its thermoneutral zone, and we have to have air exchange to remove that metabolic heat. The next important part is when we design a house, we look at the structure. We look at how do we manage the actual heat entering the house through the surfaces. So it doesn't matter if you have a very simple house like this one in Brazil, or you have a very modern tunnel house. It's a picture of a house in the United States. What we have to do is we have to design the house for the worst case scenarios. So we have to understand our local climate. So we have to understand what could we expect on the hottest day of the year with the large broilers in the house. So we need to design the house in terms of the worst case scenario. So where does heat come from in the house? We know the lights produce some heat. We know there'll be heat entering through all the surfaces of the house, whether it's the side walls, the end walls, but very, very important, the ceiling, the roof. The largest surface area in your house, apart from the floor, is going to be your ceiling. So where does the majority of the heat enter? It's through the roof. So we need to have a well-designed roof, a roof that has good insulation properties. And what I have, this image that we have looking at is the image of a open or a closed attic space. So this is very common. All the broiler houses, all the modern houses here in North America, South America, the whole of Asia, the vast majority of houses will have a false attic. So when we talk about that attic space, we got to know what is the temperature, what temperature can we expect in the attic, because that's going to determine how much heat transfer we have through our drop ceiling or our roof. So in this example, we know that that attic space can be as hot as 60 degrees Celsius. On a very hot day, if you climb into the attic, it's hot. Now, if you don't have an attic space, we're going to look at what would be the surface temperature of my sandwich panel roof. So on a hot day, that metal sheet could be as hot as 65 degrees C. So how does that affect the amount of heat gain or heat loss in the house? So when we talk about heat gain or heat loss, we need to understand the very simple calculation. Your heat gain or your heat loss in cold weather or your gain in hot weather is a function of the surface area of your ceiling. So we know that if you have a flat drop ceiling, it's equivalent of your floor space. If you have a pitched roof, you're going to have to do your calculations a little bit better to make sure you have the correct area. So area divided by the R value. Now R value is defines the insulation property of your surface and times your temperature differential. Now I'm going to run through a very simple calculation, but I'm going to do it in Fahrenheit. So don't get excited, this is very simple math. So we know that the largest surface in the house is going to be the ceiling. And we know that, for instance, the temperature of my attic space is 135 degrees Fahrenheit, 58 degrees C. And I'm going to run through an example of no insulation or very poor insulation versus good insulation. The same house, let's put in a plastic drop ceiling. Let's say we have a R value of 3, or we have a bad, really poor insulated roof. So we say the attic temperature, you could have used the surface temperature. If you didn't have an attic space, you could just assume the temperature of the roof is 60 degrees C or more. Your inside temperature is always going to be 28. I'm assuming you have a evaporative cooling system in your house. So we're going to have a heat transfer from the hot surface or the hot attic space into the house. In wintertime, it's going to go the opposite way. So let's look at the heat gain. And the surface area from this example, my house is 2,250 square meters. That's the equivalent of 24,000 square feet. I have an R value of 3. So I divide that by 3 and I multiply that by the temperature differential. Attic space is 135 Fahrenheit. My inside temperature is 83 Fahrenheit. So what is the heat gain? It's 8,000 multiplied by 52. So in this scenario, I can expect 400,000 BTUs to come into the house from the ceiling. If I simply add an insulation, a good insulation, a well-insulated roof, that heat gain drops dramatically. I can drop it down by 80%. So instead of 400,000 BTUs, I now only gain 80,000 BTUs from my ceiling. So roof insulation is very, very important. In terms of total heat production in the house, if I compare the birds with the heat through the ceiling, without insulation, our birds are producing somewhere around about 75% of the heat. 25% is coming through the ceiling. If I place a good insulation in the roof, suddenly I have to only take the 85 to 90% of my heat production is the birds, only 10% comes through the surfaces of the building. So it's very important we remove heat from the house. And why is that important? Because in every broiler house or every pullet house, every production house, which is tunnel ventilated, we have this problem of the delta T. So when we design a house today, all these numbers that I'm going to run through are all revolve around that delta T problem we have. We know that at the front of the house it's always cool, and the extraction end of the house, it's always going to be hotter. So if you ask the engineers, what delta T should I have? What can I expect? If I design my house well for very hot conditions, for the broilers in full production just prior to slaughter, I don't want to have a delta T of more than 5 degrees Fahrenheit or 3 degrees C. But in reality, a well-designed house very seldom will run a delta T in that as high as 2.8 C. I would expect it to be maybe 2, a little less than 2. So if you have good insulation in the roof, you have the correct amount of air exchange, you should be able to maintain a good delta T in your house, which means that you have a good environment. We don't have those 3 zones in the house. So what air exchange do I need to have to maintain a delta T of 5 degrees Fahrenheit? Again, a calculation. So we've got to look at, we've done the 2 calculations. How much heat was produced by the broilers? It was approximately 1 million BTUs. With good insulation, we say 80,000 BTUs is produced, comes through the surfaces of the ceiling. So your CFM, or your ventilation exchange capacity, to maintain a 5 degree Fahrenheit drop is a function of the total heat added to the house divided by that 5 degrees Fahrenheit. So the calculation is quite simple. Total heat divided by 5 multiplied by a correction factor. So it's total heat added divided by 5.3 degrees Fahrenheit. So let's look at these 2 examples. And what we're trying to illustrate is how much fan capacity does it take without insulation, or an R value of only 3. I'm going to need 3 tunnel fans. And this is, for example, the example I'm using is a 50-inch, 24,000 or 40,700 meters cube per hour fan, a standard tunnel fan. So the total heat production for the coming through the ceiling without insulation, 400,000 BTUs divided by the factor of 5.35, I need 78,000 cubic feet per minute. That's 3 fans. Now, if I was to put insulation, a good insulation, 1,000 CFM. So I'm going to need 1 tunnel fan to remove that heat portion of the heat. If I look at that portion of heat produced by the birds themselves, we said 1 million BTUs in this example, divided by that 5.35 factor, that's 194,000 CFM, 8 tunnel fans. So with a well-insulated ceiling, I'm going to need maybe 9 tunnel fans in this house to keep the delta T below 2.8 C. So in terms of fan capacity or air exchange, that is why we've come up with these numbers of fans. It's all about removing heat from the birds themselves. It's all about the wind chill effect. But keep in mind, stocking densities really play a role. So in terms of CFM per square feet, or meters cube per hour per square meter, if you have somewhere between 9, maybe 10 or 11 CFM per square feet, you're going to have a good ventilated house. So what air speeds do we need? For you guys who are in the rearing side, if you're building a new rearing facility, you're going to need somewhere closer to 500 feet per minute. If you do the calculations like we just run through, and you do the same calculation for pullets, it's going to tell you, yeah, you probably only need 2 meters per second. An air exchange equivalent of 2 meters per second. In breeders, it's going to be somewhere between 2.5 to 3 meters per second. But in broilers, we know we have to have an air exchange of approximately 45 seconds. So it means we're going to have to design a house for a small broiler for 3 meters per second. But if you went to Brazil or here in North America, all the new houses with the larger broilers are all spec'd at 3.5 to 3.75 meters per second. So how do we simply determine air velocity or airspeed? How much fan capacity do we need to create a certain amount of airspeed? And all our calculations, and maybe Brendan spoke about it earlier, when you're talking about perimeter capacities, perimeter inlet capacity. Capacity is a function of speed and cross-section. So if you know your cross-section and you know what speed you want, you simply multiply those 2 together. That will give you capacity. And when we talk about cooling cells, we always talk about, or if we talk about light traps, we'll always talk about at what speed do we size my cool pads? At what speed do I size my inlets? At what speed do I size my cool pad? It all comes back to the same calculation. Capacity is equal to velocity times cross-section or area. So what speed do we need? Sorry. How do we measure the speed? We use a very simple tachometer, a kestrel. We got to measure our speeds closer to the tunnel fans, maybe 25 meters from the tunnel fan. And for simplicity, we usually do a speed reading above the first feed line, in the center of the house, and over the others, the third feed line, or the feed line on the opposite side. Yes, we can make many readings throughout the cross section, and so for simplicity's sake, we just do 3. That will give you an average reading, which is probably a little lower than the design reading for the house. So if you want to get a very accurate reading, you're probably going to have to do a very lot of readings across the cross section, just like in the bottom right-hand side. Wind chill, always a contentious subject because we have many controllers today with algorithms which utilize wind chill, a perceived wind chill effect. Now, there's not a lot of detailed research gone into wind chill. We don't have a lot of scientific information to back it up. But what wind chill effectively is once there's going to be a difference between wind chill effect for younger birds versus older birds. And the data that I have in front of me is the wind chill effects for a 4-week versus a 7-week bird. And the surrounding temperature of the bird in this situation is 32 degrees Celsius. So for a 4-week bird at 2.5 meters per second, their perceived temperature is somewhere close to 22. But the same bird at 7 weeks, that perceived temperature is somewhere close to 26.5. So as the birds age, their wind chill effect is less. But the problem with wind chill effect numbers is we really don't take into account a couple of things. One is humidity, stocking density. So when you utilize a wind chill or you have a wind chill chart, be very careful about assuming those numbers are correct. Those numbers are based on birds in experimental conditions. How much metabolic heat are we removing from the bird? Because a wind chill effect is essentially a function of removal of metabolic heat from the chicken. Now, if the birds are tightly stocked, they're in contact with the floor, that wind chill effect will be different. So always keep in mind, it's a great tool to use, but be careful. So the next slide is from the University of Georgia. And now this was a very interesting piece of information, and it's one of their papers they published in 2019. And I just want to go through it very quickly. Is the red graph is the temperature of the chicken. It's their the bird temperatures. They put a temperature sensors or loggers into the skin of the bird. Now, what they did in this experiment, and this is over a 24-hour period, and at the bottom you'll see start at 6 a.m., finished at 6 a.m. in 24-hour period. The left axis, vertical axis, is bird temperature, measuring and that's measured in the red line, the red graph. The green graph is the actual house temperature, and the blue is the actual house humidity inside the house. So what they did is they ran 2.5 meters per second. So they have been running that and at 2 p.m. they turned off the equivalent of and reduced the speed to 0.5 meters per second. And they looked at how quickly internal temperatures rise. So over a period of only 2 hours, the internal temp went from 41 degrees C, which is what we think is normal, very quickly up to 42.6. It didn't take much time. And with high humidity, because remember in this house, the cool cells were running, so your humidity was 80 to 85%. And how long did it take for that chicken to get back to normal? 7 hours. So it increases temperature dramatically in 2 hours, but it took more than 7 hours for it to bring its temperature down to a stable level. But what we see very nice further on the right-hand side of this graph is in this section here, we have lights off. They're going into the darkness period. So what happened when the lights went off? Temperatures went up again. The birds all sat down and were in contact with the hot floor. So remember, when the lights go off, the birds are in contact with the hot surface. So this is just the thermal images taken from the paper they produced. And on the left-hand side, you can see these are the birds that during that 2-hour period, and this is how quickly they respond. Again, a very nice paper published by the University of Georgia, also looking at, they had temperature probes under the skin of the chicken. And the black line is water consumption. So the water consumption stops for a period of time. That's the darkness program. That's when the birds sit down. What happens when the birds sit down at night? Their temperatures go up. So, and the next video I'm going to show you is, just to give you a brief overview of what to expect. This is a video taken with a thermal camera with 35-day broilers in Brazil. And what we had a farmer who was only running 1.8 meters per second. He had his evaporative cooling system was on. The internal temperature of the house was 28 degrees Celsius. The relative humidity was close to 85%. So we asked him to turn on all his fans because he was trying to save electricity. He was complaining about his power bills are very high. He said, well, the target temperature of my house is 28 and I've got it. I can get it with my cool cell system. But we told him it's not about the actual temperature in the house. It's about air exchange. The only way we remove heat from the birds is through air exchange under high humid conditions. So if you look at this video, what we'll show, once we turn on those fans, the temperatures, the surface temperature of the birds change. With a thermal camera, the whites, the yellows, the oranges indicate high surface temperatures. The blues, the purples, all indicate cooler surfaces. So within about 45 to 50 seconds, we quickly see that feather temperatures change. And that's an indicator to me that with the extra air exchange, we're removing more sensible heat. So when we have high humidity, we have to have good air exchanges. Because once we get the humidity up into that 85% range, our evaporative cooling function diminishes dramatically. So sensible heat is the only way to go. And we have to have at least 2.5 meters per second. Anything below that with a stock broiler house is you're going to run into problems. So what temperature, target temperature do we need? In our broiler guide, we'll tell you we need this for the first week, the second week. And you'll notice we don't tell you anything further than 14 days. Why? Because in hot weather, it's all about perception, wind chill effects. And what you see on the right-hand side is a temperature curve, a picture of a temperature curve taken from a controller. And what you can see this grower is doing is, he's at 35 days, his target temperature is 20 degrees C. It's a lot lower than what we would typically expect. So it's all about understanding the effects of wind chill and understanding your stocking densities in your houses. Another great tool to have, if you have it, can you utilize it, is when we run tunnel ventilation, utilize sensors at the extraction end of the house. When we run cross ventilation, we use the average of all our sensors. But if you can, I'll utilize the sensors closest to, maybe the 2 sensors closest to the fan end of the house. That way, you will force the ventilation system to run based on the hottest part of the house. So again, it's very important to understand that when we look at larger birds prior to slaughter, once we had full stock, once we hit the 38, the 39, the 40 kilogram per square meter, at nighttime, it's extremely important that we continue to ventilate. So if we have a very hot afternoon, the internal temp of the birds will rise slightly. Even in a well-ventilated house, well-designed house, the birds get hot in very hot conditions. It's humid in the house, it's very hot. They start to back off feed in extreme conditions. What happens when we turn off the light, when we start to go into the evening and the temperatures drop? They go back and feed. They eat the feed they would have had in the afternoon. So they compensate for what they didn't feed in the afternoon. So when we run ventilation at night, and we got to understand we have to ventilate to get that metabolic heat out, because they've now eaten again, and they've eaten a lot of feed. So as we go into the evening, we need to maintain our ventilation to get rid of that metabolic heat. So the next little bit before we run into the last portion of the presentation is static pressure. How does static pressure change in tunnel mode? In cross ventilation mode, static pressure is the same wherever you make your reading, whether it's at the front or the center or the back of the house. But once we run into tunnel ventilation mode, static pressure readings will be different. Where the air enters the house, if you have a cool cell, we know that the pressure drop across the cool pad is going to be somewhere in the region of 10 or 12 Pascal or 0.05 inches of water column. As the air turns in the house and goes down the pipe or into the cross section of the house, that squeeze effect, we call it the transition pressure or squeeze pressure. We take in air through a large opening, we then squeeze it into a narrow pipe. That squeeze effect has a significant pressure drop. And then as we move through the house, down the house, we expect some form of pipe pressure or resistance. If you're in a breeder house, a production house, you have hoppers, you have nest boxes. They all add to your pipe pressure. When we design a broiler house, we keep it as smooth as possible to reduce the pipe pressure. So the total pressure or the total amount of work the fan needs to do to bring the air from the cooling pad to the extraction in the house is a function of all those pressures. So we have a pressure drop across the pad, let's say 12 Pascal. We have a slight increase of pressure. You could say 2 Pascal, maybe even less than 2 Pascal over the tunnel inlet curtain or door. We could have a transition pressure, maybe another 10 Pascal. So just past the cooling cells, if we measure static pressure in full tunnel mode, the pressure in that position is going to be, let's say, 25 Pascal. Now, as we move down to the extraction in the house, we've picked up some extra resistance. Reading the pressure at the fan end is going to be closer to 30 to 35 Pascal in a 600 feet per minute or 3 meter per second house. So understanding the different pressures will give you an indication of how well your house is running. So if you suddenly measure your static pressure and it's crazy high at the front of the house, maybe you have a blocked cool cell. So what pressures can I expect? And in South Africa, most of your houses will be probably spec'd for 3 meters per second or a little more. So I would expect the house to run in full tunnel at somewhere between 30 to 35 Pascal. That's if your house doesn't leak. If you have holes in the roof, this is not going to work for you. So a very nice way, if you have an older house or even a new house, run a static pressure test of all your tunnel fans. You'll be surprised what you see. So what we do with a static pressure test is we close up the house, we run 1 tunnel fan, or the equivalent of 1 CFM per square foot, or whatever that is in terms of in terms of square meters, but it's going to be the equivalent of 1 of those large tunnel fans. Run each tunnel fan, measure its pressure test. They're going to tell you how well that fan performs. And in this example, there were 8 tunnel fans. They all were pressure tested individually. And what we saw was the one in the bottom left corner was very poor. Its pressure test is very poor. That was the tunnel fan used for the timer ventilation mode. So that is the fan that ran the most. So that's why it's worn out. So you can do this pressure test on a new house and a new building, record your pressure tests. Over time, they will change and it'll indicate to you, maybe you need to change your fan belts. Maybe you need to put on new pulleys. So when we talk about a modern tunnel house, we have different inlets. Today, many of the new houses will have, and in South Africa, it's very common to see the rack and pinion doors. These are a different style of door, quite popular in breeder production houses where there's equipment close to the tunnel inlet. But most of us today will opt for a tunnel door. And the reason we go for a tunnel door is simply, and I think that's, this is at our World Technical School, I think that's Nigel on the right-hand side doing a good smoke test. And what a tunnel door does for us is it gives us really good movement in the front of the house. So what you're going to see from the smoke test is that swirling action. It looks like a wave at the sea. So with a good tunnel door, we get really good returns. So that's why, that's one of the main reasons why people are using tunnel doors today. It's that actual return we get. So once the smoke exits the tunnel end of the house, is already on the sidewalls. So we eliminate to some extent those dead spots that we typically would have seen with a curtain style inlet. So what a tunnel door does for us is helps us with the dead spot at the front to a degree, and especially here on the sides. So in a curtain-sided house, we struggle to get that return. So what we're going to find in a curtain-sided house is these dead spots are going to be a little bit worse here on the sides of the house. So it all depends on your choice. In a breeder house, reduction house, we tend to use a curtain because we have equipment close to the sidewalls. So when we design a broiler house or a breeder house, we want the house to be as smooth as possible. We want to make sure that our air velocities across the cross-section of the house are as close to equal. But as we increase speeds, as we demand more velocity in our houses, we're going to see that differential between the sidewall speeds and the center of the house increase. And this is what you typically see in a broiler house, going from 450 feet per minute up to 750 feet per minute. So have a smooth sidewall. If you have an old style of house, curtain-sided house, in Brazil, almost all the houses will have a double curtain. So the internal curtain has good function in terms of the insulation value, but also in tunnel mode, it gives you a really smooth surface down the sidewall. It's not so important. Your ceiling doesn't have to be smooth. It's your sidewalls that need to be smooth. So finally, we spoke essentially about heat removal from the birds, heat entering the house from outside, understanding static pressure, and the last portion of my presentation this morning or this afternoon is going to be, how do we decrease the temperature of the incoming air? How do we increase that differential between the actual bird temperature and the surrounding air? We have to have a cooling system. So in many of our houses today, we have an evaporative cooling system. That evaporative cooling system has one function only: get the temperature down to close to 28 degrees C to maintain a delta T of 2.8 C. We don't want to have a house, if we wanted to drop that temperature further, we would have to add a huge amount of evaporation system, and we'd have to have a massive amount of fan capacity to get it. So the best balance is a target of 28 degrees C. So what pads do we want to have? We always want to have a 45-15. And we need to make sure that when we size our cool cells, we size them at the correct velocity at 1.8 meters per second. So most of the suppliers of cool cells will tell you, size them at 1.75, 1.8. Don't size them too small because you're going to end up with higher static pressures, and don't oversize them. So when we do the sizing, we make sure we use the operating capacity of our fans that we're going to use at least 25 Pascal, because our house is going to run at 3 meters per second. So we size our pads at that higher pressure range so we don't end up putting in too much cool cell. Again, a very simple calculation. How do we size the pad? It's the capacity is equal to velocity times cross section. So your pad area is a function of your fan capacity you're going to use to achieve your specific speed divided by the pad face velocity. And that is 1.8 meters per second. So it's a capacity divided by 350 feet per minute. So when we talk about using cool cells, we know, and this is a very nice image from a controller for a farm in Thailand, what we see every day. Temperatures go up, humidities drop. So we see the cycling effect. Early in the morning, humidities are always high. In the evening, humidities are typically high. So we don't want to run our cool cells at night. We don't want to run our cool cells in the mornings. So that's why we talk about 9 o'clock till 5 o'clock. Maybe if you're in a summertime like here in the United States, where it can be very hot all the way through till 9 o'clock, yes, we will run our cool cells at night, but it's because it's still extremely hot. So when we run cooling systems, we know that for every 1 degree Celsius, we drop the temperature with the cool cells, we can expect our humidity to increase by nearly 5%. So when we run our evaporative cooling system, we have to have at least 2.5 meters per second in the house. In a pullet house, you could argue you need only 2. In a breeder house, maybe 2.5 would be adequate. So let's look at scenario. This is a house, the city in Pakistan, Lahore, and it's renowned for quite cool winters, but in summer they have extreme temperatures. Sorry. Okay, what I'm going to do is quickly run through this scenario. So if you look at any supplier cool pad, you're going to see that they will give you the expected temperature drop. Now, it doesn't matter how you run this scenario, whenever you do it, whatever your outside temperature is and whatever your outside humidity is, we're always going to end up with 80 to 85% humidity when we run a cool cell. So we have to have good air exchange. That was it. Thank you very much. And I'm sorry I ran over a little.